Let's take a look at just simplifying square roots. You've done this before, but this is just a little review. So when I want to simplify something like, say, the square root of 50, what's my goal when I'm simplifying a square root? Yeah, I want to make the part that's inside the number, inside the radical, as small as possible, right? Now, how do I do that? Is 50 a perfect square? No, and we all know what perfect squares are, right? Yeah. Perfect squares. So let's make a list over here we can refer to of perfect squares. What's the smallest perfect square? 2. Well, 2 squared is 4. So 4 is the smallest perfect square. That's 2 squared. Next would be 3 squared is, 4 squared is, 5 squared is, 6 squared is, 7 squared is, 8 squared is, 9 squared is, 10 squared is, and let's just stop it there for now. Okay, so there's a list of perfect squares. What is the square root of 36? 6, right? So a square root of a perfect square is always going to end up being an integer, right? Those are simple, but 50 is not a perfect square. So if I put that in my calculator, I'm going to get some decimal that just goes forever. Okay, never repeats, never terminates. It's irrational. So that's not what we want. That's not simple. We want to write this, though, if there is a perfect square factor of 50, we want to take advantage of that.
Is there going to be a number on the outside?
Yes. Yeah, there is. There's going to be a number on the outside, if we can simplify it, and a smaller number on the inside, right? So is there a perfect square factor of 50? In other words, is there a perfect square, one from this list, that divides into 50? We want the biggest one possible. 25, right? So we could split up 50. We could split this up into the square root of 25 times 2. Okay? Now there's a property of radicals here that we're going to use. There's a property of radicals that says the square root of a times b equals what? What can I do if I have the square root of a product? Remember? How can I rewrite this? The square root of a product, like the square root of a times b, I could write as what? No, I don't need any other letters in there. Square root of a times square root of b. So I can separate the square roots. Does that make sense? Okay, so in other words, why is that helpful here? Well, look, we can turn this into the square root of 25 times the square root of 2. And why do we do that? Why do we do that? Well, okay, true. You're right. But what's my next step? Okay, yeah. What does that simplify to? 5. Okay, the square root of 25 is 5, right? The square root of a perfect square is always going to give me back an integer. So then I just end up with 5 times square root of 2. And I'm done. Because now the 2 can't go any further, right? There's no perfect square factor of 2, right? Does that make sense? So let's try another one for practice. Okay, so let's simplify the square root of 108. Square root of 108. So my goal, I want to find the biggest perfect square factor of 108. Okay, now there is a way, I'll show you a little trick for this too. Okay, you know that, is 108 going to be a perfect square? No, the next one in line would be 11 squared, which is 121. Okay, so 108 is not a perfect square. What's the biggest number we'd have to start with looking for?
49.
It would be, okay, true, but if we took half of 108, because it has to be an even multiple, it has to be divided evenly into 108. So if 108 doesn't work, the biggest number that could possibly work would be half of 108, right? Which is 54. So 54 is not, but we can start on our list right here then, right? Because 64 is too big. That's bigger than half of 108, so it can't go into 108, right? Only think the smallest number that would divide into 108, other than 108 itself, would be 54, agreed? Yeah. So we'll start at 54 and work our way down. Well, the next perfect square in line is 49, so we can limit our search a little bit, can't we? And we always want to go in this direction because we want the biggest one. Does 49 go into 108? It's not going to, is it? 49 and 49 is 98. And so 98, there's not enough for another 49 in there, is there? Does that make sense? 2 times 49 is 98, and then there's not that much left over. I need right, does that make sense? It won't go in 3 times. What about 36? That could, maybe, right?
It goes to
3 times?
Yeah.
Okay, so 3 times 36 works, doesn't it? Right? So I can take that 108 and I can split that up then. This is the winner. That's the one, that's the biggest perfect square that divides into 108. There's some other ones. 9 does, right? And 4 does. Okay, I think 4 does, right? But those aren't the biggest ones. Now, if I don't get the biggest one, that's okay. It just means that when I'm all done, I'm going to have to do the same process again to a smaller number, so it'd be easier. But I got to go until the number inside the radical is done. It doesn't have any perfect square factors. Okay, so we'd like to get the biggest one first time if we can, so we only have to do this once rather than more than once. All right, so 108 then breaks up into, you already told me, it breaks up into 36 times 3. So let's just skip, let's take this last example. Couldn't we just skip we could have skipped maybe from there down to there, couldn't we? We could just write, once we know what the 2 factors are, let's write them as separate square roots. So square root of 108 could be written as the square root of 36 times the square root of 3, because 36 times 3 is 108, and then 36, the square root of 36 is 6. Boom, you got it. So our answer is 6 square root of 3, exactly. No big deal, right? Okay, that's not hard stuff. You're going to be fine with that. Okay, so the other wrinkle that you could maybe add to that is, what if you wanted to simplify a product of square roots? And this is no big deal either. What if I wanted to do something like, let's say, square root of 32 times 3. Square root of 32 times the square root of 3. Okay? There's a bunch of ways you can do this. You could simplify each of those radicals individually, but here's a way that and you're fine. If you want to do that, that's fine. But here's a way that always works. You can always just take the numbers under the radical and turn it into one big number, and then do what we just did, right? So 3 times 32 is what?
96.
96, good. So we got the square root of 96, and now we'll just look for the biggest perfect square factor of 96, right? So let's see, 96 is not a perfect square, right? Half of 96 is what, 48? So we're just going to work our way down from 48 in this direction, finding the perfect squares. So we missed 49. What's the next one down? 36. Oops, I want to make those red. 36, and then 25, 16. Okay, so let's go down the list. Does 36 go into 96? Doesn't, does it? So that one's off the list. Does 25? Nope. 16? Yeah, 16 does. 16 times 6, right? Okay, so we could rewrite this as the square root of 16 times the square root of 6, and what's the square root of 16? 4. We got it. Okay?
We do all of this?
Yeah. Okay, let's do another one. How about square root? We'll do, okay, square root of 8 times square root of 18. It's going to be a big one. Okay, so what's 8 times 18? Now, don't use your calculators. Do this in your head. Just get used to this. This is good. How would I multiply 8 times 18? Okay, go. 8 times 10 would be 80. 8 times 8 would be, so 80 plus 64. 144. And that's a perfect square. What is that? 12. Yeah. Boom. Okay? Make sense? Good. Okay, so what about simplifying quotients of radicals? So what if I had something like this? What if I had square root of, let's say 36/25. Okay, thank you. So how am I going to deal with that? Square root of 36/25. Now remember what our trick was. If we look back a couple slides here, let's see, we had a trick up here, didn't we? We had a pretty cool trick where if we had the square root of a product, we could break it up into the product of the individual square roots. We can do the same thing.
Go to the square root of 36 and square root of 25.
Aha, good. So we could write this as the square root of 36 over the square root of 25. And what's the square root of 36?
6.
What's the square root of 25? Done.
Would you divide that to simplify it?
That is simplified,
Oh, sorry.
right? We can't, we would simplify the fraction if we could,
Yeah, sorry.
but we can't. Well, give you another example. How about, what if we had instead the square root of 72/50ths? Okay, now this time we could split it up, but we can always use another trick too. In this last one, 36/25 didn't reduce as a fraction, right? If you can reduce the fraction, that's a good idea. Make it smaller before you have to mess with the individual square roots. What about this one, 72/50? Does that reduce? Is there a number that divides into both of those that I could divide each by? 2, they're even, aren't they? Right, I could divide each of those by 2 and trim that fraction down, right? So that would be equal to the square root of, what's 72 divided by 2? 36. 50 divided by 2. And then it just became the last problem that we did, right? Make sense? Okay? Okay, another one. Get a little harder one. What if we have the square root of 9/5? Now, I can't reduce 9/5, can I? So I'm going to break it up into separate square roots on the top and bottom. Okay. Okay. What's the square root of 9? 3. Square root of 5, I'm stuck, aren't I? That can't be simplified. Okay, so now there's a trick, because there's a rule. There's a rule that you can't have a square root stuck in the bottom of a fraction. Okay, we have to rationalize the denominator. That's what we say in math. But what that really means is I just have to get any square roots have to end up on the top, but not the bottom.
Would you just square it?
You can't just square it, because if I square it, I'm going to get a different answer, right? I'm going to get a different, like for example, what if my answer ended up being 2/3? Well, if I square that, I'm going to get 4/9, which is different. So I can't square it, but I'm going to do something like that. Say it again. I'm going to multiply, not by the reciprocal, I'm going to multiply both the top and the bottom by the same thing. So I'm really just multiplying by 1. I'm not going to change the value, I'm just going to change the look of the answer, right? I'm going to multiply the top and the bottom by the square root of 5. Okay, now let's see why that works. If I multiply the top and the bottom by the square root of 5, what am I going to get on the bottom? Now think about this. What's the square root of 5 times the square root of 5?
5.
That's 5, isn't it? Because if I multiply something by itself, isn't that the same thing as squaring it?
Yep.
Right? So think what that means. If I'm going to take the square root of 5 squared on the bottom, what do square roots and squares do to each other?
Yeah.
Cancel. They're opposite processes, aren't they? Right? Inverse processes. So we can cancel those out. Another way of thinking of it is the square root of 5 times the square root of 5 is really just the square root of 25, which is what? 5, right? I think it's easier to think of it this way, though, don't you think? If I multiply a square root by itself, it always just undoes the radical, right?
Yeah.
So I end up with a 5 on the bottom, what do I get on the top? Well, 3 times the square root of 5, right? Does that make sense?
Yeah.
And this is just a product, I just multiply straight across. And so that's my answer. My answer is 3 times the square root of 5 over 5, and I can't simplify that anymore. Like if that were a 6 on the bottom, for example, 3 over 6 could be reduced, but it can't this time. Now, why is that better? It's a good question. Really, it is a good question. Why can't we leave a square root on the bottom? You ought to be able to, honestly. This is kind of a relic. This is an old math, almost a custom, but we do it. And like on the Oaks test or on your placement test, on the compass test at the end of the year, you're going to have to know how to do that, to write a simplified fraction that involves square roots. And so the rule is, it's very simple. The rule is just you always multiply the top and the bottom of the fraction by whatever the stranded radical is. By stranded, I mean the one that's stuck on the bottom, okay? Yes?
So it wouldn't matter if it was on top? Stuck on
It doesn't matter, if it's on top, it's fine, you just can't have it in the bottom. Okay, so try one of these, try another one for practice. What if you had something like this? What if I want you to simplify the square root of 18 over 50? Okay, what about that one? Now, first of all, can we reduce that fraction?
Yeah.
We can, can't we? So let's do that. Wouldn't you agree this would be a lot easier if we could deal with smaller numbers? So what can I divide both of those numbers by to make them smaller? 2. Good. So I end up with, and while we're at it, let's go ahead and split this up, huh? So I end up with the square root of 9 on the top and the square root of 25 on the bottom, right? That's not the one I really wanted to do. Huh. Oh well, what's that one end up being? 3 over 5. I didn't mean to do that. Let's pick a different one. Okay, what I really wanted to do probably was something like this. How about square root of 18 over 75 would be good. There you go. That is good. I like that. Okay? Okay, can I reduce those? Not that it's essential that I reduce those, but I could a little bit, couldn't I? Can you think of a number that goes into both 18 and 75? 3 does, yeah. Remember, there's our trick, right? If I add up the digits, they're divisible by 3. 1 plus 8 equals 9, which is divisible by 3. 7 plus 5 equals 12, which is divisible by 3, right? So I could divide each of those by 3. So what do I get on the top then? Square root of 6, good. On the bottom I get square root of 25. Okay, make sense?
Could you further?
I couldn't go any further than that though, could I? 6 and 25 is as far as I could go. So then I'm stuck with, on the top, square root of 6. On the bottom I get 5 and I'm done. I don't have a radical on the bottom this time, right? Make sense? Okay?
Wait.
Yeah.
The reason why you're left with the square root on top is because that one can't be down.
Right, that one couldn't get trimmed down at
So
all.
because the 25 could go down to the square root of 25 is 5, you just get rid of it?
Yep,
Okay.
yep, exactly. So that one ended up being an easy one after all, after we reduced it. Okay, another one. Okay, what about that one? Can that fraction be reduced?
Yeah.
Doesn't look like it, does it? 75 is divisible by 3, but 8 isn't, right? And 4 won't go into 75, obviously, right? Because 75 is odd and 4 is even. Does that make sense? So we're kind of stuck with that one, aren't we? So we're going to split this up top and bottom separately, though. We can do that. Square root of 8 over square root of 75. And let's simplify the top and the bottom as much as we can. And then if we're stuck with a radical on the bottom, we've only just got that one last step to do, right? So on the top, what's the biggest perfect square, if any, that divides into 8? 4. Everybody agree? I could write that as, on the top, I can write that as square root of 4 times square root of 2. And on the bottom, is there a perfect square that goes into 25? Oh, I mean, it goes into 75, whoa, no. 25 maybe, huh? Okay. So I get square root of 25 times square root of 3, right? So what am I left with on the top then? 2 square root of 2, okay? And on the bottom, 5 times the square root of 3. Okay, so let's move down here. We're gonna have to go from there though, aren't we? Because what's the problem here? I got a stranded radical on the bottom. So what am I gonna do then to get rid of that stranded radical on the bottom? Square root of 3 over square root of 3, right? Top and bottom by square root of 3. Gotta treat those both equally. So we multiply top and bottom by square root of 3. And what do we get? On the bottom, I get 5 times, what's that equal to? What's square root of 3 times square root of 3? 3. So that becomes a 3, and I've just got 5 times 3, right? 15. Good, so the bottom is 15. On the top, I get what?
6.
Okay, I get this stuff right here becomes the square root of 6. Yeah, and then so I've got a 2 out in front times the square root of 6. And now I got to look at that and see, okay, can I do anything? No, I can't, right? The 6 can't go anywhere. There's no perfect square factor of 6, and 2 over 15 can't be reduced, and so that's my answer. Make sense? No big deal, right? We can do that stuff. Okay, why are we doing this? Why? This seems like an odd thing to do. This isn't even really algebra. This is pre-algebra review. But there's a reason we do this, and here's what it is. These are skills we need to solve different kinds of quadratic equations. Now, the good news is these are easy ones. These are easier than the factoring ones. We know how to solve factoring ones. Like, what if I had something, I'll give you an easy factoring problem. What if we had x squared plus 4x plus 3 equals negative x minus, plus 27. Okay, this is stuff we talked about the other day. Now, how would I go about solving this thing? Okay, combine like terms. And I want to put it on the side where the x squared term is positive, right? I'm going to push everything to the left, and this is putting it into standard form, where it's set equal to 0. So I'm going to end up with an x squared. How many x's am I going to get? 5. I've got to add x from this side. So I'm going to get plus 5x, and then I'm going to subtract 27, right? Agreed? So I'm going to end up with, what's that, minus 24 if I start with 3 and subtract 27. Okay, so now it's in standard form, right? And now we got the possibility of factoring it, right? This is not one where I can isolate x, though, is it? Because I've got separate x squared and x terms. There's not a single x I can point to, right? So we're stuck, we're stuck trying to factor this. Well, if it factors, what's the look going to be? Okay, so like that, right? And the first term of each in this case is going to be what? X. And the magic numbers, if they exist, have to multiply to, okay, if the positive and negative, they're going to multiply to what number? Negative 24 and add to 5. Everybody got it?
Yeah. 8 and negative 3.
8 and negative 3. That's it. Plus 8 and minus 3. And so then our solutions would just be, remember, this is the zero product property now, right? I know that I'm going to multiply this times this and get 0 when this factor is 0. So when x plus 8 equals 0, my product would be 0. Or when x minus 3 equals 0, and that factor is 0, I could also get 0 for an answer. So what are my solutions then? X equals negative 8 or x equals positive 3. Okay? So we know how to do those, but sometimes we don't have to factor. Sometimes we get lucky and we get quadratic equations that don't have two x's. Okay? We get stuff like this. what if I had, for example, let's say I had 2x squared minus 3 equals 47. Okay? How many x's are there in that equation? There is a single x I can point to. And remember what the rule is. If there's a single x that I can point to, I can always isolate it. And the way I isolate it is just by reversing order of operations, right? So if we start with our order of operations tree, it always tells us the order in which we have to do the operations to get that x by itself, right? Okay, so I want you to think about this. How are we going to do that? What are the steps in order I'd have to go through? Get that thing by itself. What do you think?
Yeah.
First I have to add, it looks like. Add or subtract. What am I going to add? Add 3. Okay, so I'm going to add 3 first. That's going to get rid of the 3 on the left. And what's the next thing I'm going to do? Divide by 2. Okay, good. So let's check those off. Let's go down the list and check those off. So step 1 was add 3 to both sides, right? So we get 2x squared equals 50, right? Step 2, you told me, was multiply, divide. So we're just going to divide each side by 2, right? And I get x squared equals 25. Okay, now what? Oh, okay, and that's on my list, isn't it? Square rooting is exponents. How about that, right? So step 3 is I'm going to undo exponents, right? By square rooting, but you got to be a little bit careful with this one. Got to be a little bit careful with this one now. When I do step 3, I end up with x equals 5. Half credit. No, 5 works. I can put 5 in my original equation and check it, and it works. 5 squared is 25, times 2 is 50, minus 3 is 47. But there's another answer. Negative 5. Negative 5 will also work, won't it? Because negative 5 squared is also 25, isn't it? Right? Okay, so there's a rule here we have to follow. The rule is that whenever you square root, whenever you solve an equation like this, when you're isolating x and you square root both sides of an equation, you always have to put a plus or minus in front of the result. Always. Okay, so that means right here, we need a plus or minus.
How do we write that in Moodle?
In Moodle, what's going to ask you, good question. In Moodle, it's going to say, write all solutions. If multiple solutions exist, separate them with commas. So in Moodle, we would just write something like 5, comma, negative 5, or negative 5, comma 5. Okay? But the important thing is there are 2 of them there. Now, why is that? You got to remember, I'm going to show you why this is. And a lot of times books don't even include this. But I think it's kind of good to know. Hey, what do those phones do now? Put those away, please. Put them in your pockets. Pockets. I don't want them out. They'll be a distraction. Put them in the pockets. Okay, so why is that? Now we know whenever we square root both sides, we have to introduce the plus or minus. It's an easy thing to forget at first, but I'll hammer on you about that. You'll get them wrong if you don't do that in Moodle too. Here's why it is though. There's a missing step. Now wouldn't you agree that when I'm trying to get from here down to there, I'm just square rooting both sides, right? Square rooting undoes a square. So I've got the square root of x squared equals the square root of 25. Okay, now what is the square root of 25? That's just 5, isn't it? That's just 5. Okay, here's the one that's a little strange. What in the world is that? The square root of x squared. Okay, it seems like it ought to be x, but it's not x. I'll prove it to you. Let's look at this for a second. The square root of x squared. Okay, think what this does. Now, if that equals x, right, then doesn't that mean that if I put in, for example, x equals negative 9, I should get negative 9 for an answer, right? Does that make sense? Okay? Or if I put in negative 5, I should get back negative 5. If this is equal to x, it should have the value of x, right? Let's try that. If I put in positive 5, Let's see what happens. 5 squared is 25. Square root of 25 is? Well, that works. So far, so good. So far, it seems like it's x. Square root of 5 squared is 5. Let's try negative 5. The square root of negative 5 squared. Well, what is negative 5 squared? 25. Square root of 5 is? 5. Okay, so when I put it, what does that sound like? I put in a positive number and it doesn't change it, but I put in a negative number and it makes it positive. There's a function that we've dealt with that does that, though. True, but there's a function that does that. What's that function called that we worked with earlier in the year? And its only job, its only job is to make sure that the output is positive. If it's already positive, it doesn't do anything to it, but if it's not positive, it makes it positive. What was that called? Absolute value. That's it. Okay, so there's the hidden step. The square root of x squared is actually equal to the absolute value of x, right? And so really what we get here is the absolute value of x equals 5. Now think about that equation. If the absolute value of x is 5, we did a bunch of stuff like this also. Remember that when we solved equations like that, if we had something like the absolute value of x equals 5, remember what we said? We said that whatever's inside the absolute values either equals 5 or whatever's inside the absolute values equals negative 5, right? So either x equals 5 or x equals negative 5. Remember that? So going back to this page then, that's why we get the plus or minus there. Okay? It's because really what you've got when you take the square root of both sides is the absolute value of x equals 5, not x. So x could be either positive or negative 5. Do you have to do that every time? Absolutely not. You can just skip from this step right here down to that step right there. But you got to remember the plus or minus. And just remember that's included. Okay, so let's try another one of those. Let's try a harder one. But even the hard ones aren't very hard. Okay, let's try one like this. What if we have 2 times the quantity 3x plus 4 squared minus 3 equals 41. Okay, that is as hard a problem as I could possibly give you, honestly. If you can do this one, you can do any of them. Now, I want you to think about, before we do anything, let's just rehearse in our minds the steps we're going to go through to solve this thing for x, to isolate x. What are we going to do first? No, we're not going to distribute. Now, I'll tell you why, and that's a common, I can see why people would say that. I can't distribute this 2 because this quantity is actually being squared. Okay, so I can't, does that make sense?
Well, could you like distribute it and then square those answers?
Okay, now I could square these answers out and then distribute everything, but then I'm going to get a really hard problem. I'm going to get a problem that's going to look like some number times x squared plus some number times x plus some number equals 0, and it may or may not even factor. And if it does, it's going to be a bear to factor because it's got a not equal to 1. So I could, but that's not advisable. This is much easier. Yeah, but you had an idea. Okay. Yeah, if I want to get the x by itself, and here's the rule we can follow, right? Remember that if I can point to a single x, I can isolate it by reversing order of operations. Right? So the first thing would be add or subtract. Yeah, the first thing we'll do is we'll add 3 to both sides. Right? Okay, so let's just block these out as we go about it. So first we'll add 3 to both sides to get rid of that. Right? Then what? Divide by 2. Exactly. I've got 2 times this quantity. If I divide both sides by 2, I can cancel that 2 out, right? So I'll divide by 2, both sides by 2. Good. Now we're down to there. Now what? Square root, right? I want to undo that radical, so we'll square root. And that really gets rid of the parentheses even. We don't even need them anymore after that, do we? Then what? What would we do next to get that x by itself? Yeah, now it's starting to look easier. Now I just subtract 4, right? Would be the next thing. So subtract 4, and then Then what? Divide by 3. And we got it. X is by itself, right? If we just follow those steps in that order, we're going to get X on the left by itself. On the right, we're just going to get whatever we get. Just some number, right? Okay, so let's do that stuff now. This would be a good place to end. Okay, so first thing you said was add 3, right? So we go first step, add 3, and that gives us 2 times the quantity 3x plus 4 squared equals 44. Good. Okay, divide by 2. So the next step is divide by 2. And would you agree if I divide by 2, both sides? I can cancel those 2's, and the reason I cancel those 2's is because they're common factors. The 2 on top is being multiplied by this stuff. I can cancel common factors. I can't cancel things that are being added or subtracted, but I can cancel things that are being multiplied, right? Make sense? Okay, so then after step 2, we end up with the quantity 3x plus 4 squared equals, what's 44 over 2? 22. Okay. Next step, square root. Step 3 is square root both sides. So if I square root both sides, that's going to undo that squared, right? And I end up then with, after 3 steps, 3x plus 4. Now, I don't need the parentheses now because nothing's being done to that anymore as a group, right? And on this side, I'm going to get what?
11.
Okay, I'm going to get plus or minus, right? Got to include that plus or minus. The square root of 22, which doesn't even reduce, does it? There's no perfect square factor of 22. 4 won't work, 9 won't work, 16 won't work, right? That's okay though. Square root of 22 is fine, that's a number. And now what do we do? Okay, minus 4. Now here's an important step. Everybody watch this very closely, because here's where I can save you some hassle. Now really I've got 2 answers here, don't I? And so technically you might think, okay, well we got to split this up. I've got the equation 3x plus 4 equals positive the square root of 22, or 3x plus 4 equals negative the square root of 22. And I can do that. I can split them up and solve them separately. But watch this trick. If when I subtract the 4, isn't that the same as adding negative 4 to both sides? Subtract. If I put the number that I'm adding in front of the plus or minus, not on the other side, don't put the minus 4 out here, put it in front. Watch what happens. Then we end up with step 4 looking like 3x equals negative 4 plus or minus the square root of 22. Well, that gives us both answers in one there, right? Negative 4 plus the square root of 22 would be one solution. Negative 4 minus the square root of 22 is the other. Now, there's one more step to do, though. What's that? Divide by 3. Okay, and so then we're there. If I just divide both sides by 3, the 3's cancel, and this is what I get. I get x equals negative 4 plus or minus the square root of 22 all over 3. And so there's 2 solutions in one, aren't there? In Moodle, when I enter these, I would have to write it this way. In Moodle, I would say one answer is negative 4, and I can split the fractions apart if I want to, but I could say negative 4 plus the square root of 22 all over 3, comma, negative 4 minus the square root of 22 all over 3. Right?
Yeah.
Now that's not that bad, and that's a really hard problem. I mean, if we expanded this out, I'm going to get a horrible looking quadratic equation that would not factor. Okay? Does that make sense?
Yeah.
Okay, that's a lot of stuff.
It's actually not that bad.
But that is easier than factoring, though, isn't it? I mean, I think you got to agree that's easier than factoring.
It is.
At least hard factoring.